Good morning, good afternoon, good evening, everyone. We'll go ahead, get started with our presentation for the day. We're very excited to have our November presentation 2024 on brain-machine interfaces in assistive robotics, clinical and engineering perspectives. We have two speakers today, Dr. Takafumi Yanagisawa, who is a medicine professor, neurosurgeon, Institute of Advanced Co-Creation Studies in the Department of Neurosurgery at Osaka University. Professor Yanagisawa is a professor at Osaka University's Institute of Advanced Co-Creation Studies and a neurosurgeon in the Department of Neurosurgery. His research specializes in clinical neurophysiology, brain-machine interfaces, and neurofeedback, with applications in epilepsy, Parkinson's disease, and assistive technology. Our second speaker today is Oscar Ege Aydogan, who has an MS in robotics engineering and is a research assistant in the Graduate School of Medicine at Osaka University. He's a robotics engineer and research assistant at Osaka University's Graduate School of Medicine. He specializes in brain-machine interfaces, human-robot interaction for neurorehabilitation, and is currently developing a BCI system to enhance motor recovery and support post-stroke rehabilitation. So I'm going to turn it over to our esteemed speakers today, who are going to walk us through brain-machine interfaces. Oscar, Dr. Yanagisawa, can you share?
I think all's good. We'll start.
Okay.
I can start.
Perfect. We see that.
Sorry, I need to change something. Sorry.
Yes.
Hello, everyone. So
Yeah.
I'm Oscar Aydogan. I'm working as a research assistant at Yanagisawa Laboratory at Osaka University. Today I will talk about brain-machine interfaces in assistive robotics, but not clinical, based on engineering and robotics perspectives. My slides include three main sections. First section is a general idea of the BMI in assistive robotics and what are the current problems and solutions. And secondly, I will talk about Professor Yanagisawa's relevant previous research about BMI in assistive robotics. And then I will end up with my current project, but in not details, like as an overview, because it's an ongoing project and collaborative project. So as an introduction of BMI, as we know, there are many problems we face, mainly like over 50 million stroke survivors live with motor impairments. So in these cases, some researchers develop exoskeletons or prosthetic devices. But for efficiency and human-robot interaction, the BMI has a huge role on these applications because it enables the real-time and task-oriented therapy to restore the independence for those post-stroke patients and for the recovery. And it plays a role as a transformative solution from the brain signals to the robotic systems. And as a rehabilitation purpose, we can say the BMI-driven robotics has significant importance as for recovery for stroke, spinal cord injuries, and neurodegenerative disorders. And the figure 1 explains the general idea about how we transfer the EEG signals from the brain to the robotics devices to command after signal processing feature extraction and signal classification steps. When we look at the global research trends about these BMI-based robotics, we can find out the recent studies shows that the DMD improves the precision and responsiveness in BMI robotics. And although the current system says like wearable or grounded exoskeleton systems in robotic perspective, BMI integrated exoskeletons has a huge advantage over those exoskeletons by having enable motor recovery for stroke rehabilitation. And also recently, some researchers work on the integration BMI to the portable devices to increase the accessibility globally. When we look at the clinical success, we can say the trials show up to 30% motor recovery improvement based on the BMI integration to the robotic rehabilitation robots and also the assistive robotic systems. So when we check the clinical success, also task-oriented designs mainly enhance the engagement and outcomes of the studies. But there are many challenges, such as like scalability requires balancing advanced designs with cost-effective production for global deployment, and also inter-user variability in neural signals still is still an obstacle for us to robust and adaptable BMI performance for our robotic studies. When we look at the one of the Professor Yanagisawa's previous papers is about the training in a use of brain-machine interface controlled robotic hand improves accuracy decoding two types of hand movements. The paper mainly focused on the enhancing robotic hand control via BMI training. And the figure 3 shows us the system overview diagram, how we control the robotic hand using MEG sensors and real-time control, and give the visual feedback to the patient. And also the figure 4 and figure 5 demonstrates the performance graph of the proposed method, and also the comparison between the improved correct rate of real and sham decoders. And also the figure 5 shows the cortical activity maps based on the real feedback and sham feedback and pre or post stages. So the study announced that the motor accuracy, the success rate improved from 28 to 50% in a 10-minute training session. And they found out that neural activity patterns became more specialized for hand movements. Although they couldn't find any significant improvement on sham decoder, they emphasized the importance of real-time feedback using this sham decoder system for enhancing the robot hand control. The second paper of Professor Yanagisawa's focus on the fast, accurate, and interpretable decoding of EEG signals using dynamic mode decomposition. So they found out that dynamic mode decomposition achieves a decoding accuracy of around 81% for movement classification. And they also revised the testing time is reduced to approximately 15 milliseconds per sample. And based on their decomposition neural signals and speed and accuracy comparison between the L2 SVM and L1 STM, mainly comparison between their proposed gram matrix STM and the other studies, shows that 10% and between 10 and 15% improvement in classification accuracy compared to traditional high gamma power features. And as a third paper of Professor Yanagisawa mentioned about BCI training to move a virtual hand reduces phantom limb pain. So for this study, they realized the real training reduced pain by 32% on day 4 and 36% on day 8 compared to baseline. And although they couldn't find any significant improvement on sham training session, but they realized the pain reduction effects were sustained for up to 5 days post-training. And the left figure demonstrates the system overview setup, like how the MEG system works. on the patients, and the right figure shows us the comparison between the pain reduction trends and pre-training and post-training sessions between day 1, then day 2, and day 3. So I will mention my current project. However, I will not be able to share the results because it's ongoing and collaborative project, and also they are still under analysis. But I will propose the overview and the main characteristics of the study. So the project mainly about dual model BMI for real-time robotic arm control. As I mentioned before, like there's a strong as you know, the stroke impacts like 89 million people annually, and with 50% experiencing chronic motor impairments that limit independence. And currently they use single model BMIs, and these systems has lack adaptability for multi-step tasks like object manipulation. And in this project, we try to adapt the dual model instead of the single model to enhance the adaptability. So in proposed solution, we are developing a dual model BMI system integrating SSVP and P300 for real-time robotic control. And SSVP will ensure the continuous robot arm selection and then the continuous object selection. That it will enhance the picking and the placing time of the continuous robotic sequential cycles. And ongoing objective of the project, we are planning to design and evaluate the BMI system to support multi-step robotic operations for rehabilitation. Especially the main motivation is enhancing the motor skill training and functional recovery for stroke patients. When we look at the system overview, mainly there are two steps, we can say, the robotic interface step and BMI step to be able to make us to control the robotic arms in simulation environment. So in our approach, we are planning to use and also currently use like 4 different pre-curve frequencies for each robotic arm. So the main system has 4 robotic arms, and these robots are needs to take the objects from the table and move to the designated area. And in this movement, we are aiming to increase the motor training and functional recovery of the stroke patients. So, and for P300, we are using a ERP triggered by target stimuli, and which is colored cubes in 4 different colored cubes on the table, and this is for cognitive-based object selection. For a sequential task, is mainly from robotic arm selection using SSVP, then color cube selection using P300, and then robotic manipulation for picking and placing the objects. So the bottom figure demonstrates the overview of the system configuration from the users, then browsers, and the robot environment server. And when we look up the EEG data acquisition and processing setup, and we have 3 channels for SSVP for occipital cortex, and we use 5 channels for P300 for parietal and sensory parietal regions. For signal processing, we can say for pre-processing steps, we use filters like notch filter, 60 Hz, and bandpass filter for 3 to 30 Hz, and CER we are using. And for SSVP, we are detecting the frequency via phase Fourier transform. And for P300, peak amplitude extraction from the ERP responses. And for classification, for signal processing, we are using linear SVM classifiers for real-time decoding. And this figure represents the simulation environment of the robotic manipulation system. And there are 4 main robots, and the patients will be able to select each robot by using SSVP-based filtering queues. So we set the different frequency values for each robot, and user will be able to select robotic arm by focusing the SSVP-based queues. After that, the patient will select which cube colored in that robot environment will be selected. based on the curve stimuli guide the robot to select the corresponding cube using P300 responses. And after that, the selected cube from the selected robot will be able to pick the cube and move to the same curve area. And this will repeat until the last cube from the last robot environment will be replaced from the table to the site areas. But with patients, we'll be able to the sequential, like they will decide the order, which robot will pick which cube in what order. So we are aiming to make the functional recovery for the patients. And for communication protocol, we are using the LSL for real-time data transmission. And for the feedback mechanisms, normally we can say like the selected robot arms will be highlighted upon SSCP confirmation to make the selected robot more visible for the patients. And also when the patients will select the cube, they will confirm visually, like they will be the frame, they will in the frame and core intensity change. And of course, these are happening after pitch value detection. And as a progressive display for feedback for the patients, we are developing the countdown timers for the task initiation and feedback adaptation for the patients, and also real-time display of the task completion percentage for user motivation is proposing, because the patients needs to see how much they need to continue to finish the task to make them the eligible time management for them, and also the for instructions. And for the adaptive interface, we are adjust the threshold based on the user performance, and we decided that the SSVP for each 10 to 20 trials and P300 for each 30 to 50 trials. And for a future set of this project, we are aiming to finish the robotic arm control using BMI and dual system using SSVP and P300. And also we will be enable the post-stroke patients for functional recovery. So thank you for listening. Unfortunately, I will not be able to show the results because they're under analysis, and it's under a collaboration between the company. So in the future, maybe after the publishing, I can be able to demonstrate them and present them. Thank you for listening. If you have any questions, I would like to answer, of course.
We'll wait to do questions
after
once everything is done.
Okay.
Professor, you're up. You can share your screen.
Okay. Okay. Can you see my slides?
Yes, yes.
Okay. Thank you for this opportunity. I'm Takumi Yanagisawa. Today, I'd like to talk about how we implement the BCI or BMI to treat the phantom limb pain. So, phantom limb pain is the neuropathic pain characterized by the pain in the amputated limb, or pain that follows partial or complete deafferentation, such as brachial plexus through avulsion. So it is rather a common pain after the trauma of the upper limb, and it happens more than 80% of the lost limb patient, and mostly they suffer, and 50 to 80% of them suffer in the pain, severe pain. And these are characterized. These schemes characterize how they feel the pain. So because there is no limb, but they feel something like a still existing limb, and it feels like this kind of painful situation. And the origin of the pain has been attributed to three parts. So one is the amputated part, and the other one is the spinal cord, and the sensory motor cortex in the brain. So the basic concept is the phantom limb pain is caused by the loss of sensory motor function of the limb, and that causes the maladaptive changes in the sensory motor cortex in the brain, and that causes the pain, especially. So we want to reorganize the maladaptive sensory motor cortex to relieve the pain. And so far, several methods has been proposed to change the activities in the sensory motor cortex to relieve the pain. For example, the mirror therapy trains the patient to activate the sensory motor cortex of the lost limb by watching the phantom hand, which is the reflection of the image of the actual hand. And the aim of this mirror therapy is to imagine the phantom hand movement using the actual hand movement, and to induce the activities of the motor cortex related to the phantom hand. And similarly, the training can be done using the augmented reality, which can visualize the phantom hand at the stump of the lost limb. So this training to move the phantom hand was intended to induce the reorganization of the sensory motor cortex to reduce the pain. Although these trainings are aiming to change the cortical representation, it has been determined, it has not determined whether we should strengthen or weaken the cortical activities related to the phantom hand to reduce the pain. So there are two conflicting hypotheses of the abnormal activities. One is the deteriorated motor cortical activities of the phantom hand causes the pain. So in this case, increasing the representation of phantom hand will decrease the pain. The other hypothesis is the residual representation of the phantom hand causes the pain. So in this case, decreasing the residual representation will decrease the pain. So apparently, these hypotheses are oppositely conflicting each other, but we didn't know which hypothesis is true. And to unveil the desired cortical representation to reduce the phantom limb pain, we used the brain-computer interface, or BCI, to change the phantom hand representation and pain. So using the BCI, we induce some plastic changes on the sensory motor cortex relating to the phantom hand, and we observe the pain, how the pain changed by this representational changes. And as Dr. Osgar mentioned, we have developed BCI using magnetoencephalography, MEG. MEG can detect the tiny changes of the magnetic field generated by the neurons, and it has high temporal resolution compared to the fMRI, so that it is appropriate for online control of the decoded information. And actually, the decoded hand movement were used to control the robotic hand like this. And for example, this patient cannot move his right hand due to the brachial plexus shoulder version. And but when he tried to move his paralyzed right hand, his left sensory motor cortex activated like this. So when you imagine grasping, his left hand was activated, and this activation was detected by the MEG and decoded, and this robotic hand was controlled. And here, to decode the hand movement, we need to apply machine learning technique to the recorded MEG signals. At first, we record the MEG signals while the patient moves their front hand to be grasping and opening at the interactive timing trigger. And these are the example of the cortical activities of the right amputee while he moved his right front hand. The cortical currents were estimated by the source estimation method called VBMEG. As you can see, the left sensory motor cortex was activated for the grasping and opening state. And if we compare the two activation by the F value, we can see the high F value on the contralateral sensory motor cortex. That means the cortical current on the contralateral sensory motor cortex has the information of the grasping and opening state. And actually, when we apply the machine learning technique, actually in the SVM here, we can classify the phantom hand movement with the accuracy of about 70%. And also we can classify the real hand movement with accuracy about 80%. And we can and then we apply this decoder and decoding method online, and we could control the robotic hand through the online MEG signals. And the patient were placed in the MEG scanner, and the online MEG signals were recorded and decoded, and the robotic hand was controlled. And the patient watched this movement of the robotic hand through the monitor. And we instructed the patient to control this robotic hand by moving their phantom hands. And here is the experiment protocol. So we trained the patient to move the robotic hand by using their phantom hand. And we compared the pain before and after the training, or actually the training of 10 minutes. And we also recorded the phantom hand and the MEG signals during the phantom hand movement before and after training. And here we used the two types of the decoder to control the BCI. One is the phantom hand decoder, which was constructed using the MEG signals while the patient moved their phantom hand. The other one is a random decoder, which was constructed using the same MEG signals, but the label was randomly shuffled. So this is the result of the training effect. So before BCI and after BCI training, the phantom hand, in case of the phantom hand decoder, the contralateral sensory motor cortex during the phantom hand movement was increased. Sorry. On the other hand, the random hand decoder and the contralateral sensory motor cortex activation was not changed, not significantly changed. And the pain intensity evaluated by the visual analog scale. Actually, the pain intensity was increased after the phantom hand decoder training. On the other hand, it didn't change after the random decoder training. So the simple reconstruction of the motor function of the hand did not decrease the pain, and actually it increased the pain. So we did another decode training to decrease the phantom hand representation. So in this case, we made another decoder, which is called a real hand decoder. This decoder was constructed using the MEG signals during the intact hand movements. And using this decoder, the patient was instructed in the just same way in the previous study. So patient controlled the robotic hand by moving their phantom hands. So to control this robotic hand, the patient need to induce the real hand activation, but while they are thinking about the phantom hand. So it makes the changes of the phantom hand representation to the different representation. And actually, after the training to use the real hand decoder, the contralateral sensory motor cortex activation was decreased after training, and the pain also significantly decreased. So as a summary, we did the neurofeedback training using the 3 different decoders, and we according to the different decoder, the pain significantly changed. Actually, after the training using the phantom decoder, pain significantly increased, but after training using the real hand decoder, pain significantly decreased. So even the patient did the same experiment, same training, by changing the decoder, we could control the pain significantly. And also the decoding accuracy from the MEG signals also significantly changed after training. So the phantom hand decoder significantly increased the decoding accuracy, but the real hand decoder significantly decreased the decoding accuracy. So to decrease the phantom hand, it was suggested to decrease, we need to decrease the phantom hand representation. So as in terms of summary, the BCI training significantly changed the pain depending on decoders, and that changed the classification accuracy of the phantom hand movements. And then we applied this BCI training with real hand decoder for consecutive 3 days to evaluate the sustainable efficacy of the pain reduction. So here we use the virtual phantom hand image instead of the robotic hand to enhance the patient motivation to do this training. The phantom hand image was created by the flipping the image of the patient intact hands. And again, the real hand decoder was used to control the robotic hand, this image. And again, the patient was instructed to control this virtual phantom image by moving their phantom hand. And in case, for case of the sham training, we used a randomly changing value from 0 to 1, which controls this image. And we compare the pain intensity after training using the randomized crossover trial. So this is the pain changes during the 3-day training. So for the real training, the day 1, the pain before training was about 40 or among the 100 in visual analog scale. It significantly decreased after the training of 1 day, day 1. And in the day 2, again, the pain was significantly decreased after training. In day 3, there was no significant differences after training, but the pain before the training was significantly decreased from the day 1, the pain before the training in day 1. So it seems that the pain gradually decreased in the 3-day training. On the other hand, in the sham training, there were no significant differences after training. And also this is the, and after 3-day training, we evaluate the pain for 20 days in their home. And actually, the pain significantly decreased compared to the sham training and real training after 5 days of the training. So day 4, day 5, 6, and day 8, there was significant decrease of the pain compared to the sham. So we could see that the 3-day trainings sustainably reduce the pain for 5 days after training. And also, we compared again the decoding accuracy of the phantom hand movements before and after training. And we see the significant decrease of the decoding accuracy in the real training. And the decrease of the decoding accuracy was correlated to the decrease of the pain. So again, as a summary, 3-day training of BCI use significantly reduced the phantom limb pain for 5 days after training. The pain reduction was correlated with the reduction of the decoding accuracy of MEG signals during the phantom hand movements. And the induction of the cortical reorganization by the BCI training was effective to reduce the phantom limb pain sustainably. So, using the BCI technique, we can unveil the relation between the cortical representation and pain so that the appropriate training to cure the phantom limb pain. So as a conclusion, the induction of the cortical reorganization by the BCI training was effective to reduce the phantom limb pain, and the BCI is able to visualize and manipulate the cortical representation of the phantom hand to understand its function. So this is the collaborator and the funding, and thank you for your attention. And I'm happy to have a question.
Thank you, Professor. Hi, everyone. This is Michelle. Thank you, Oscar, as well. That was a really interesting presentation. I had a couple of questions of first clarification and then application. So my first question for Oscar, in terms of relating what you did to what the professor just presented, you mentioned P30 and SSVEP signals. Are you using the same brain imaging or brain data collection procedures? I was a little confused.
Yes, I mean, I'm currently applied. Previously, I was using like SVM method, but then I changed to SSVP and P300. So
are you using MEG? Are you using
no EEG? EEG
oh,
data.
so you're using
data
EEG,
sets. Yes,
and the
yes.
professor was talking about MEG data acquisition. I think that's important to clarify. Can you talk to what are the differences in the two? I mean, one is clearly a little bit more portable. Is the goal to map what the findings from the MEG to an EEG more portable paradigm?
I don't work on MEG systems, so I only work EEG. So maybe the comparison the professor can make better the comparison. So sorry.
So, MEG has the higher spatial resolution because EEG can be distorted by the tissue differences, but the MEG is not so much affected by the tissue differences. So we can evaluate or estimate the cortical activity more precisely using the MEG. So for the purpose to understand what signal or what kind of neural representation affecting to the pain or affecting to some diseases, the MEG will be much good way to use it. But as you mentioned, the MEG is a huge and a very expensive equipment. So we cannot use it for the clinical practice, actually. So the EEG would be much better to distribute it for the clinical practice. So we are now using the EEG for the clinical application also.
So to clarify then, so that's really, so the EEG now, in terms of thinking about how it could then be portable, what do we lose in terms of the brain computing interface accuracy? Because I thought it intriguing that you were saying decoding accuracy was related to pain decrement. And so is the decoding accuracy related to the fact that the person is unable to accurately imagine their phantom limb, doing the grasping or, controlling the hand as time goes on? I was a little confused in terms of the mechanism by which this relationship was occurring.
Right. So, MEG is good for the visualization, or MEG can precisely reconstruct the actual activities of the brain. But when we decode the signal, we use the machine learning technique. So machine learning does not need to visualize the activation. So machine learning just only need the information. So if there is some statistical difference, machine learning can detect the information. So in that sense, EEG also has the information or difference of the state, brain, the grasping or opening state. But although it is not good for the visualization, but it has also the information. So to use the, to decode the information, EEG also good for the application. And imaginability. So ask the question. So how the decoding accuracy changes among the patient. So that's important point. And actually, the decoding accuracy weakly correlate to the how much the patient can move their phantom hand. So, for example, if we count the speed of the phantom hand movement, so for example, we can instruct the patient to move their intact hand just similar to the phantom hand movement in their mind, and they can represent the phantom hand, something like very slowly or quickly. So we can count how much the patient can move the phantom hand, and that ability was weakly correlated to the decoding accuracy. So it actually related to the behavior.
So what is then the mechanism by which the pain is decreasing? Because
Right.
I thought that was fascinating. So what could you explain a little bit more, maybe the underlying mechanism as to how that actually is happening, and then how could that then be used in terms of, the clinical application?
Right. That's the actually not clearly unveiled part. So, but
Okay.
the hypothesis is that the some kind of the prediction error caused the pain. So this is the hypothesis. So, for example, when the patient lost their limb, they they and when even lost their limb, they still have the motor command in their brain, and they try to move their lost limb, and the motor command generated to control the lost limb. But because there's no limb, there's no feedback of the sensory feedback was not will not come back to the brain. So there must be some prediction error. So between the actual motor command and feedback sensory signals, and that prediction error, one hypothesis that prediction error caused the pain or worsened the pain, and so the remaining residual motor command cause the pain or worsen the pain. So to treat that, there's two strategies. And one is to decrease the motor command, or other is to increase the sensory feedback. Okay. So we can reconstruct the hand with the sensory feedback that might reduce the pain, but maybe that's costly things. We need some surgery or very big limb. So the other way, just reduce the motor command, would be kind of the practical way. So we are taking that strategy to reduce the motor command and reduce the prediction error and might decrease the pain.
Thank you. There are a couple of questions in the chat. So Delani asked, is this only for the reduction of phantom limb pain of the upper limb? How about applicability of this for lower limb amputations? And he talked about because the functional area of the brain for the upper limb and the lower limb is different. So can you translate what you're doing to the lower limb phantom limb pain?
Yeah, that's a important point. Actually, lower limb phantom limb pain is much more common than the upper limb, and we want to apply it for the lower limb. But yeah, we haven't tested yet. So as you know, the limb area is located in just the middle part of the brain. So the left limb and the right limb representation are located very closely. So it is a little bit difficult to record or separately record these two activities. So it's a little bit challenging for the MEG to discriminate two activities. So we haven't test this method for the lower limb pain, but yeah, it's very interesting point. So yeah, we want to try it.
Thank you. There's another question in the chat. So this is from Dr. Wamsley. She asked, she commented, great work. She has two questions. The first for Oscar. In your current study with the stroke population, you are using the occipital and the parietal areas of the brain. Why not the motor cortex of the motor task? Was her first question.
Yeah, thank you for the question. Actually, it's a good question. So the main reason actually, so we are not using the motor-related features. We use task-specific features. For example, the reason for occipital cortex is for SSVP signals, because the patients will choose the robots by eye movements. So the flickering cues, so like visual stimuli. So we don't need to use the motor activity for that. And for the selection of the cubes, it will happen by the P300 signals. So it's kind of like the parietal cortex region area. So like the target object. So we just need to select the target based on the instruction to the patient. Actually, I forgot to mention during the presentation. So during the instructions of the experiment, we represent the display as a red color or blue color. And when the patients see the colored picture, they focus that color. And then when they think the visual that we show them, the red color, the robot will take the red color cube. So that's why, I mean, there's no motor related features. So just visual stimuli, and just visual stimuli works on. So that's why.
So I would just have a follow-up question, because in stroke, one of the challenges is to relearn the movement of the upper extremity in this case. And so, and to basically try to recode or, you know, induce plasticity around the movement of the upper extremity. How does that, your technique induces then upper extremity recovery?
So in our system, I didn't I propose to recover for the actual neck movements, because based on the eye movements and the head movements to the robots, I'm just planning to recover the neck area, actually not the upper limb area. But the reason,
okay.
yes, the reason why don't use motor cortex also, like when we use the EEG signals from motor cortex, sometimes we have lower spatial resolution. And so when we use SSVEP and P300, these signals provide more robust and reliable.
So why the stroke population? It seems like this application might be more appropriate for
Alright.
like a spinal cord injury, or high level, people that have a lot of like neck challenges, because usually maybe that's not as prevalent in the stroke population. I'm just curious as to like why stroke versus some other paradigm.
It's a great question. That's the main motivation for the project, still under processing for me. So I'm
Okay.
searching for the novelty for the papers. So that's why the stroke patients have lots of injuries and the general area in the world. So that's why I picked the stroke, and I can explain in what I explain. But I think I can focus other spinal cord injuries also patients. So I'm just trying to focus which part of patients would be better for the project.
Okay. There was a question, a simple question. Maybe in the chat you can put the definition of DMD. Someone wanted to understand that. And then
I can say if you want.
Yeah,
like
maybe put it
diabetic.
in the
Okay.
chat, could be
Okay.
helpful.
Okay.
And then there was a question that says maybe back to the professor Dr. Takafumi, like the question was asking, could you clarify the decoder of the real hand? I believe this was the second scenario. Is the individual thinking of co-activation or of activation of the real hand, or actually moving the real hand to decrease the phantom hand?
Yeah. So during the training, they don't move the real hand, and actually they don't move any body part.
Okay.
So it looks like they are still.
So
But
are they thinking about moving then?
thinking about only phantom hand movement. So in their mind, they are moving their phantom hand, but the actual body are not moving. Okay, and to construct the decoder, we record the MEG during the real hand movement. So at first the patient do the real hand movement according to some instruction, grasp and open, and we record the MEG signal of that hand movement, and that recording was used for the construction of decoder. Okay, so decoder pick up the cortical activity similar to the real hand movement. So and in the training, patient tried to control the robotic hand by moving their phantom hand, but the decoder tried to pick up the activity similar to the real hand movement. So, so the patient need to induce the representation similar to the real hand movement while they are moving the phantom hand movement. So this strategy makes to change the phantom hand representation, because naturally when the patient the phantom hand, their phantom hand movement representation appears, but it doesn't move it is not suitable to control the robotic hand, because the decoder is picking up the real hand movement representation. So yeah, that's
interesting. There are we're running out of time, but there's actually another question in the chat. There was from Ebenezer at Adams. Is there a specific phantom hand decoder technology I think it's an implementation question that could be considered suitable for Africa, because there is a huge unmet need in the management of pains associated with stroke in Africa.
Yeah, right. So this strategy is used for the control of the disease related to the representation, motor representation. So there are several diseases related to the motor representation, but for the purpose of to reduce the pain, so there's many chronic pain, so something like a low back pain or yeah, yeah. So to reduce the pain, we can use some other technology or other method. For example, in our recent study, we control the insular activity, which represent the pain intensity, and by changing the insular activity, we could succeed to decrease the, increase the pain threshold of the pain. So using the neurofeedback to target the other brain region, maybe we can extend the um, eh, applicability of the BCI to treat the pain. So yeah, so maybe yeah, just same as Japan, we have many pain patient. So we would like to make the many different neurofeedback to treat different diseases.
Do you see the future in this? We're at 8 o'clock, but I just had one kind of general question. The future of BCI as kind of a truly accessible tool that could be applied in low resource settings globally, or are we kind of, is it like a tool that is primarily for just the research part, just studying in general, but is it, do you see that this could be possible?
Yeah, I think it's possible. So, because recently neurotechnology industry very rapidly growing, and the main part is the growing of the device part, and many devices are developed, and the cost for the devices are decreasing. Actually, there's many good device to detect the high precise signal with the low cost. So I think we can apply the EEG or such low cost technology and using the AI technology to detect this, to extract the information from this small sample, small channels. So yeah, using combining the AI and such devices, the kind of accessible device will be on the market, I think.
If someone wants to contact you, can you, if you're willing to share your email
Sure.
in the chat, if anyone wants to kind of directly follow up with you, maybe if our colleagues on the call in other places where this technology is not available would like to touch base to maybe start a collaboration around something, then they are able to. Thank you. So same, Oscar, if you're willing to also share your email so people can touch base with you if they need to. I am going to just say thank you and leave the last word to Rochelle.
Oh, this is
Thank you so
fantastic.
much.
Thank you both so very much. Very informative. And thank you for adjusting to our time differences as well. We hope everyone enjoyed this. We will be running our December webinar again in the third week, on the third Wednesday of December. We'll send that information out shortly. And we look forward to seeing all of you over there.
And that one will be back to the regular time. We adjusted the time because our colleagues were in Japan, which is very, very far ahead of us here in the East Coast. So the December will be back to 5 p.m. CAT, right? Which is 10 a.m. EST.
Yep.
And it will also be on amputations, lower limb, but we'll kind of talk about the some accessible prosthetic design for the lower limb. Thank you guys.
Thank
Take
you
care.
all.
Bye.
Thank you.